In late 1950, inside a conference room in Moscow's Kurchatov Institute, a Soviet engineering delegate dismissed the
Even the
latest American
Americans cannot
announcement with a sneer
industrialize
that found
physics.
its way into internal memos. A reactor built in under a year? Impossible. Even the Americans cannot industrialize physics. Their assumption was absolute. In the Soviet worldview, a nuclear reactor was an artisanal construct, a machine that required years of sequential design, verification, and material preparation. To them, it was a monument of scarcity, the culmination of hard-won expertise developed under tight constraints after the war. The idea that the United States, still presumed by many in the USSR to be undisciplined in scientific organization, could compress this timeline into months seemed delusional. This confidence came not from arrogance alone but from precedent. The Soviets had spent half a decade battling shortages of high-purity graphite, nickel alloys, and uranium compounds. Even Obninsk, their future achievement, was projected as a multi-year project requiring incremental design stages. Within their system, even small experimental reactors took 3, sometimes 5 years from approval to operation. Thus, when American agencies floated the claim that a new reactor, an experimental breeder, would go from approval to criticality in under 12 months, Soviet analysts categorized it as American public relations theater, another capitalist exaggeration to intimidate the socialist world. And so, in 1950, the mockery continued. A senior Soviet reactor designer reportedly commented that a nuclear plant cannot be accelerated by throwing workers at it, an ideological axiom forged by a society where manpower never translated into instantaneous productivity. To Soviet planners, reactor physics required deliberation, not speed. Metallurgy required patience, not abundance. Construction required sequencing, not concurrency. They believed these principles were universal laws, and that America was bound by them as rigidly as they were. But they misunderstood the country they were mocking. While Soviet scientists pointed to bottlenecks as immutable laws of nature, American laboratories and industrial contractors were already preparing designs, machining components, training operator crews, and fabricating sodium cooling loops before the final blueprint was even approved. The Soviets saw chaos. In reality, they were witnessing a new species of industrial warfare, one born in the Manhattan Project, hardened in the assembly lines of Willow Run and Kaiser shipyards, and now pointed directly at the atomic future. In February 1951, the United States broke the world's assumptions. Approval was granted, ground was broken. Components began to arrive simultaneously from 5 states, and Soviet intelligence recorded the moment with confusion. Someone in Washington had decided not to wait. Designs would be finalized during construction, fuel plates would be machined before the neutron flux map was complete. Logistics would move with wartime tempo. Nothing like this existed anywhere in the USSR. The Soviets had laughed because they believed nuclear development lived inside the slow, careful rhythm of their own industrial limits. But the Americans had spent the past decade proving that industrial limits were not natural laws. They were design problems. And now, for the first time since Hiroshima, the USSR was about to learn that the United States possessed a secret weapon even more terrifying than a bomb: speed. To understand why Soviet planners felt so certain, so unshakably confident, that America could never compress reactor construction into 9 months, One must step inside the logic of a system engineered under scarcity. Soviet nuclear development after 1945 emerged not from industrial abundance, but from a nation clawing itself back from the devastation of war. Every gram of high-purity graphite, every kilogram of uranium metal, every vacuum pump or chromium alloy tube carried the weight of scarcity economics. As a result, the USSR built doctrine around frugality, sequential engineering, and centralized expertise. They believed this doctrine was universal. They believed the Americans were bound to it just as they were. In the Soviet mindset, nuclear reactors were handcrafted. Their designers lived inside a world where metallurgy labs were overstretched, machine shops were understaffed, and reactor components often required custom fabrication at facilities that still used pre-war tooling. Lead times for critical parts were not measured in weeks but in quarters. The Soviets therefore assumed that any country, regardless of wealth, would face similar constraints because they misinterpreted scarcity as a natural property of nuclear engineering rather than a reflection of their own industrial limitations. This logic shaped their strategic forecasts. Soviet analysts predicted that American reactor projects would mirror the rhythms of Obninsk and the early RBMK prototypes, a multi-year crawl dominated by theoretical verification, drawn-out material testing, and slow component delivery. Their intelligence estimates claimed it would take the U.S. at least 30 months to operationalize a new experimental reactor, even under ideal funding. They assumed committees, safety boards, and interagency disputes would compound delays. In their worldview, complexity inevitably slowed progress, because complexity slowed them. What they ignored was the fundamental asymmetry between the two systems. The Soviet model depended on concentrated expertise, small groups of elite physicists solving problems within a bottlenecked industrial base. The American model depended on distributed capability, dozens of national labs, hundreds of contractors, and thousands of Manhattan Project-trained machinists capable of executing atomically precise work at factory scale. Yet Soviet planners continued to assume parity. They judged American capability through the lens of their own constraints and concluded with academic certainty that reactor construction could not be accelerated by simply allocating more factories, more workers, or more parallel processes. Their theoretical models reinforced their assumptions. Soviet engineers believed reactor design required a rigid step-by-step progression. Neutron flux mapping finalized before vessel fabrication, thermal hydraulic models validated before coolant loop machining, fuel metallurgy stabilized before mass production. They assumed deviating from this order was impossible. To them, concurrency was recklessness masquerading as engineering. But America did not inherit these limitations. The U.S. emerged from World War II with an industrial doctrine built on concurrency, modularity, and redundancy. A doctrine that allowed aircraft, ships, and weapon systems to be produced before the last design revisions were even locked. This was a nation that built a Liberty ship in 4 days, a B-24 every 63 minutes, and plutonium reactors at Hanford before final theoretical models were complete. The Soviets saw chaos. America saw throughput. Thus, the flaw in Soviet logic was not arrogance, it was calibration. They believed reactor development was constrained by nature, by physics, by complexity. They never considered that it was constrained only by the industrial system behind it. When the U.S. announced that an entirely new reactor, experimental breeder Reactor Number 1, would begin construction in 1951 with the goal of reaching criticality the same year, Soviet analysts dismissed it because their entire strategic worldview said it could not be done. They were not wrong within their own frame of reference, but their frame of reference was too small. America was about to demonstrate that a reactor was not a monument of scarcity. It was a product, and products, when a nation commands the largest, fastest, and most flexible industrial base on Earth, can be built at speed. The Soviets miscalculated because they saw only the visible parts of America's nuclear program. The laboratories, the universities, the figurehead scientists. What they did not see, what their intelligence services consistently underestimated, was the invisible infrastructure the United States had built during the Manhattan Project. A fully integrated, industrialized nuclear ecosystem capable of manufacturing reactor components with the same tempo and precision that Detroit once reserved for engines and aircraft. America's true advantage was not a breakthrough in physics, it was a breakthrough in organization. By 1950, the U.S. possessed not merely nuclear laboratories but an entire production civilization dedicated to atomic work. Hanford had proven that large-scale, continuous plutonium production was possible. Oak Ridge had demonstrated high-volume isotope separation, mass spectrometry, and reactor fuel metallurgy on an industrial scale. Argonne had already become the command center of reactor design theory, while Los Alamos retained the world's densest concentration of nuclear theoreticians. And perhaps most critically, the Idaho desert, remote, secure, and flush with wartime funding, had quietly transformed into a sprawling proving ground, the National Reactor Testing Station. This was a country where reactor-grade metal casting, high-purity uranium fabrication, neutron flux instrumentation, and sodium coolant technology were not rare, artisanal specialties. They were product lines. During WTUNS, America had mobilized over 500,000 workers for the Manhattan Project across 30-plus sites. When the bombs fell and the war ended, the expertise did not evaporate. It calcified into an industrial heritage. Tens of thousands of machinists, welders, metallurgists, and technicians who had once produced calitrons, diffusion barriers, and reactor graphite blocks now moved into the post-war nuclear industry. They carried with them production habits forged under wartime urgency, overlapping schedules, rapid prototyping, and the confidence to machine components before theory had fully settled. This was the invisible advantage the Soviets never accounted for. The moment the U.S. authorized experimental breeder Reactor Number 1, EBR-I, in February 1951, the machinery of this atomic industrial civilization roared back to life. Argonne drafted the reactor's conceptual design even as Idaho teams prepared the construction site. Manufacturers in Ohio began machining fuel cladding before the final fuel geometry was chosen. Companies in California worked on sodium cooling pumps while engineers in Illinois were still refining thermal hydraulic models. Metallurgical teams at Oak Ridge pre-tested uranium alloy batches weeks before Argonne finalized the neutron economy calculations for a fast breeder core. The Soviets observed these steps with bafflement because their system could not replicate them. Their reactor programs depended on narrow pipelines of expertise that moved sequentially. America's system moved like a net, wide, parallel, interconnected, redundant. If one contractor fell behind, 3 more could replace it. If one lab hit a theoretical snag, another lab solved it. If a machining shop needed retooling, wartime-era precision plants, once dedicated to B-29 engine casings, could be repurposed overnight. No Soviet facility had a comparable depth of atomic-capable subcontractors. The Soviets did not understand the scale that made 9 months possible. They did not understand that America's industrial base could fabricate multiple reactor vessels simultaneously and select the best one. They did not understand that procurement for EBR-I leveraged existing Manhattan Project inventories, valves, pressure fittings, shielding materials that had already been mass-produced. They did not understand that America's wartime logistics doctrine, refined through millions of tons of Lend-Lease and Pacific Theater supply chains, had reshaped domestic infrastructure such that shipping a reactor vessel cross-country was no more exotic than transporting an airplane wing. To the outside world, EBR-I appeared as an experimental scientific instrument. To the United States, it was a culmination of a decade-long experiment in industrial mastery. When construction began in the Idaho desert, the reactor did not rise from plans alone. It rose from a national ecosystem primed for atomic speed. Each weld, each pump, each fuel plate reflected a capability the Soviets never saw. The capability to build nuclear infrastructure like a nation builds ships, aircraft, and engines. This was the hidden American weapon the USSR never planned against. An industrial base so large, so agile, so technically saturated that even a reactor could be treated as a fast-moving production task. The world believed reactor construction was slow because the world had never seen a country industrialize the atom. But America had already done it, years before the Soviets realized what that meant. The shock began with a date, February 1951, authorization to construct an entirely new type of nuclear system, a fast breeder reactor using liquid sodium coolant. A machine so experimental that even the most optimistic American engineers privately estimated an 18 to 24-month timeline. Yet the Industrial Operations Division at Argonne National Laboratory proposed something that sounded impossible even to some within the U.S. government. Completing the reactor, assembling its coolant systems, machining fuel, installing instrumentation, and achieving criticality all within the same calendar year. To the Soviets, who monitored these announcements through scientific journals and intelligence intercepts, it was fantasy. No nation, especially not a decentralized capitalist one, could coordinate reactor metallurgy, systems engineering, and site construction with such compression. Soviet planners filed their assessments. The Americans were exaggerating again. Then the numbers began to arrive. Construction crews poured concrete for the EBR-I foundation within weeks of the authorization, while the pressure vessel was already being shaped in a Midwestern facility that had once mass-produced naval gun components. The sodium cooling loops, normally a multi-year development due to purification standards, moved at an unprecedented pace because the United States had carried wartime alkali metal research into the nuclear era. Purification columns, electromagnetic pumps, and stainless steel piping were fabricated by contractors accustomed to supplying thousands of parts to aircraft factories. What the Soviets assumed required surgical, artisanal effort, the U.S. achieved through industrial repetition and redundancy. The timeline compressed further. By late spring 1951, fuel element production began at Oak Ridge and Argonne concurrently. Uranium casting lines designed during the Manhattan Project to handle rapid throughput delivered the first alloy batches before reactor assembly had even reached the halfway point. The Americans were not waiting for perfect conditions. They were sequencing tasks with a logic unfamiliar to Soviet planners. Construct, refine, install, test, and correct simultaneously. And on December 20th, 1951, the impossible happened. Criticality. A fully functional reactor, authorized, built, assembled, fueled, and tested in 9 months. Achieved self-sustaining nuclear fission deep in the Idaho desert. The next day, on December 21st, 4 light bulbs glowed from nuclear-generated electricity, the first in human history. This was not propaganda. This was physics powered by logistics. The Soviets scrambled for explanations. Their internal analyses, declassified decades later, reveal the disbelief and confusion. One Soviet memo asked how the Americans had bypassed the standard reactor metallurgy bottleneck. Another questioned whether U.S. safety protocols had been suspended. Still another theorized that diversions of military labor must have artificially accelerated construction. What they failed to grasp was that America's industrial base, the same force that had once built Liberty ships faster than U-boats could sink them, had simply been repurposed for atomic work. Consider the raw data. The United States moved the reactor vessel to Idaho in under 10 days, a logistics feat impossible in the USSR due to rail constraints. Sodium coolant purification reached operational readiness in under 2 months, compared to Soviet early fast reactor loops that required 6 to 10 months of continuous processing. Instrumentation calibration, a notorious time sink, was reduced to weeks because multiple subcontractors produced identical parts, allowing replacements on demand. Most devastating to Soviet assumptions was fuel fabrication. Soviet metallurgy labs required highly sequential processing, often slowing production because each casting line could only operate under the supervision of elite specialists. America had entire teams, dozens of trained metallurgists, working in shifts. Soviet reactors depended on the availability of a handful of experts. The U.S. had factories full of them. The Soviet shock deepened when they discovered how Argonne achieved design concurrency. Core configuration was still being modeled while the vessel was welded. Fuel geometries were finalized while the first batches were already in casting. Thermal hydraulic parameters were refined as the sodium loops were installed. To Soviet engineers, this was madness. Yet to American engineers steeped in W-H-2 production doctrine, it was merely standard practice. A chilling realization spread through Soviet scientific circles. America was not building reactors as scientific projects. America was building reactors as industrial products. This realization produced not only scientific alarm but ideological collapse. The Soviet belief that socialism held the advantage in disciplined scientific progress shattered in the face of a capitalist system that could mobilize thousands of workers, hundreds of companies, and multiple laboratories in a synchronized rush toward atomic power. A Soviet reactor physicist years later summarized the heartbreak. "We optimized equations. They optimized factories." EBR-I was more than a reactor. It was a strategic revelation. The United States could convert theory into infrastructure at a speed no other nation could match. The USSR realized too late that America's strongest weapon was not the bomb itself. but the ability to mass-produce the future. The 9-month reactor was not just a technological demonstration, it was a blueprint. EBR-I's success in 1951 signaled to American strategists, naval planners, and industrial architects that nuclear power could be scaled, standardized, and, most importantly, accelerated. What had once been viewed as a decade-long scientific endeavor could now be treated with the same tempo as aircraft procurement or shipbuilding. The psychological impact inside the United States was profound. For the first time, the atomic age looked not like a laboratory-bound enterprise, but a manufacturing ecosystem waiting to be industrialized. This realization reshaped Cold War strategy. Almost immediately, Admiral Hyman Rickover seized the opportunity. The proof that reactors could be built in months, not years, became the philosophical foundation of the U.S. Navy's nuclear propulsion program. The Shippingport Atomic Power Station, commissioned in 1957 as the world's first full-scale commercial nuclear plant, drew directly from the industrial processes validated by EBR-I: modular construction, parallel fabrication, pre-tested subsystems, and contractor redundancy. The speed of EBR-I enabled Rickover to demand and receive accelerated supply chains for naval reactors, culminating in the USS Nautilus, which went from keel-laying to nuclear-powered sea trials in astonishing time. Without the precedent of the 9-month reactor, such ambition would have been dismissed as recklessness. Meanwhile, Idaho's National Reactor Testing Station transformed overnight. EBR-I demonstrated that small modular reactors could be produced with factory-like discipline, so the U.S. expanded its roster. In the following 2 decades, Idaho would host more than 50 reactor projects, experimental, military, and commercial prototypes, making it the densest concentration of reactor development in world history. Each project rode on the momentum of EBR-I's lesson. Speed is possible because the industrial base already exists. The Soviets, watching this cascade of projects, struggled to understand how the Americans were able to pivot so quickly from one reactor generation to the next. Their own development cycles still followed multi-year design and validation phases, constrained by bottlenecks in material science and machining. Even when the USSR finally deployed Obninsk in 1954, it had required years of calibration and incremental testing. By the time Obninsk lit its first kilowatt-hour, the Americans had already demonstrated fast breeder technology, moved into pressurized water reactor standardization, and were laying the foundations for a nuclear-powered navy. America's strategic legacy came from one truth. EBR-I proved that the United States could industrialize nuclear technology faster than any other nation could prototype it. This was not merely a production advantage, it was a deterrent. The USSR understood that even if it matched American breakthroughs in theory, it lacked the capacity to convert them into hardware with comparable speed. In a world where nuclear submarines, power reactors, and plutonium production cycles determined geopolitical weight, speed of implementation mattered as much as scientific discovery. EBR-I also redefined civilian energy policy. The demonstration that nuclear power could be made operational rapidly convinced American utilities and policymakers that atomic energy was not an exotic scientific toy but a viable component of national energy infrastructure. By the early 1960s, reactor orders surged, and American manufacturers such as Westinghouse and GE began treating nuclear reactors as catalog products. Standardized containment vessels, heat exchangers, and control systems emerged from industrial lines that once produced wartime hardware. The Soviets could only watch this acceleration with growing unease. Their best scientists could match American theoretical work, sometimes even surpass it. But the industrial tempo, the capacity to operationalize, was out of reach. A reactor that took 9 months to build represented a structural advantage the USSR could not close, no matter how many engineers it trained or how many institutes it opened. The legacy of 1951 was therefore not a set of glowing light bulbs in the Idaho desert. It was the strategic realization that nuclear power, like aircraft, ships, or electronics, could be mass-produced. The 9-month reactor became the silent foundation beneath decades of American atomic supremacy. Years later, a Soviet nuclear theorist would capture the lesson with stark honesty. "We believed the Americans built bombs. We did not understand they had built an industry." The story of EBR-I is not merely a chapter in nuclear history. It is a revelation of how nations win technological eras, not through isolated brilliance, not through individual scientists or elegant design philosophies, but through the ability to convert knowledge into hardware at scale. The United States, more than any other nation in the mid-20th century, had mastered this conversion. And the 9-month reactor stands as the purest expression of that mastery. For decades, geopolitical analysts attempted to quantify American power through the lens of GDP, military budgets, or headcounts of scientists. All of these metrics mattered, but none fully captured the force that reshaped the Cold War. The American doctrine of industrial concurrency. When the U.S. set out to build EBR-I, it did so with the full muscle memory of World War II, an era when assembly lines replaced academies, when engineering success was measured not only by correctness but by throughput. In that world, a reactor was not sacred. It was solvable. It was manufacturable. The Soviets had never seen science treated this way. In their universe, nuclear physics was an elite craft conducted by intellectual aristocrats under severe material constraints. Every test, every casting, every simulation bore the weight of scarcity. Their scientists were brilliant, but their system forced brilliance to move slowly. They optimized what they had: careful sequencing, methodical validation, and meticulous theoretical modeling. They believed this methodology was the universal cost of participating in the atomic age. EBR-I shattered that belief. The shock was not simply that America built a reactor in 9 months. The shock was that America built it the way it would build a warship or a factory, through parallelization, redundancy, rapid iteration, and a network of industrial suppliers that dwarfed anything the USSR possessed. For the Soviets, the realization was existential. If reactors could be built like mass-produced machines, then America's strength lay not only in its physics but in its very economic structure. The contest was no longer between two groups of scientists. It was between two civilizations with different manufacturing realities. And in that contest, speed became strategy. The implications rippled into every domain of Cold War competition. The United States deployed nuclear submarines faster than Soviet naval bureaus could redesign theirs. It fielded commercial reactors while the USSR was still wrestling with scaling issues. It built test reactors, naval prototypes, power stations, research cores, and fast-spectrum machines at a rate that made Soviet planning documents obsolete before they were even printed. Reactor by reactor, facility by facility, America demonstrated that innovation is not a moment. It is a pipeline. This was the deeper legacy of EBR-I. It proved that atomic power favored the nation with the largest industrial chassis. Once that truth became clear, the Cold War entered a new phase. Scientific races would continue. Ideological battles would intensify, but the underlying asymmetry remained immutable. America did not just create nuclear technology. America created the ability to manufacture nuclear technology. Its national laboratories became not only centers of scientific inquiry but command hubs for mega projects. Its contractors learned to treat atomic components with the same production discipline as jet engines. Its universities trained not only physicists but thousands of machinists, engineers, and technicians who could execute at scale. This is why EBR-I matters. It is not remembered because it lit 4 light bulbs in the desert. It is remembered because it was the moment the world saw how the United States intended to lead the atomic age. Not by theorizing faster, but by building faster. In the long arc of Cold War history, this was the turning point, invisible to the public yet unmistakable to every Soviet analyst. When they plotted the timelines, design authorization in February, criticality in December, they understood the strategic meaning. They understood that America's industrial base was not merely productive. It was transformative. It could turn strategic intent into physical infrastructure with a velocity no socialist economy could match. One Soviet scientist, writing anonymously in a private memo years later, captured the essence of the shock with a single line that has since echoed in Western archives. "We thought we were racing their scientists. We were racing their factories. And that was the race the world had already lost."